Okay, so we had quiz 4 last week. I'll just go over that real quick. What is the true statement about latches and flip-flops? Latch is level sensitive, that's true. Flip-flops cannot be designed flip-flops cannot be designed with an always statement. That's a little confusing, but flip-flops can only be designed with an always statement, so that's not true. Flip-flop is level sensitive, not true. Multi-bit latch is called a register. That is not true. Multi-bit flip-flop is called a register. And a latch cannot be reset, not true. So answer is A latch is level sensitive. What's the next state function of state bit Q0 in the circuit below? So for this one, you have to start with the Q0 flip-flop and look at the input, which would be the next state. And so the next state function is, well, there's something ANDed with something. The first input to that AND is Q1 or Q0. So Q1 or Q0, and then that's ANDed with A. Okay, and that's for Q0, right? And then I have the answer here for the other 2 bits as well. I have the next state logic for those as well. But the question only asked for next state logic for Q0. Right? In the circuit below, suppose we set the A input to constant 1 and then pulse the reset input. What is the state of Q2, Q1, Q0 in the 3rd cycle? Recall that the S and R register inputs indicate set and reset respectively. So yeah, these, it is possible to have a set input. It's not common, right? But a set would just force the output to 1. So when we reset, we're going to set Q2 and reset Q1 and Q0. So that should be a 1, 0, 0. So that's filled in there, right? So I got 1, 0, 0 is our reset state. And then for the next state logic, Q2 is just not A, right? So yeah, so Q2 will be 0 because we assume that A is 1 as in the description there. It's a constant 1. And then Q1, the next Q1 is Q2 and A. So Q2 and A. Q2 is 1, so that's 1 and 1. So that would give you a 1. And Q0 is the function that we derived in the last slides, which is Q1 or Q0. So that would be 0 or 0 and A. So that would be a 0, right? Make sense, right? And so now once you have the next state will then become the current state in the next cycle, and then you just repeat that same process. So you calculate the next state as a function of the current state and any inputs, when in this case we just had a hardwired input. A was hardwired to 1. Okay. Okay, so then this one says it gives a sorry? Oh yeah. Answer was 0, 0, 1 and 0, 0, 1. Yeah, I think so it obviously gets stuck there because any state that's 0, 0, 1 will give you a next state of 0, 0, 1. So you get trapped into that state. Okay, this one gives a finite state machine diagram, and it says what's the output of the next state logic with inputs S1 equals 0, S0 equals 1. So with those values of S1 and S0, that means you're in state 0, 1, which is this state, and A is set to 1, which is going to transition us back to the 0, 0 state. Right? Did I do that right? Oh, I don't have an answer there, but 0, 0, right? You guys can double check me on that, right? So state is, S1 is the most significant, the first bit, S0 is the least significant, so 0, 1, so we're in this state, and A is set to 1, so we're going to follow this transition. So our next state is 0, 0,
What was the answer?
0. The output of the next state logic 0 0.
But there were 3 bits, I think.
Let me see. It's possible. Connect. Just my luck that my password expired today, so I'm probably gonna have to delete the Wi-Fi and re-add it. How about this? Let's connect to USC guest.
I'm asking because I had 0 0 0 and it's wrong.
It should have been multiple choice, was it?
It was.
Oh, okay.
Yeah. But they were all 3 bits.
Oh, so there are 3. Let's see, there was 3 on the previous one, right? Hold on, let's go back here.
Yes, there were 3.
Yeah, this one just has two state bits, but let me see what I had in the quiz.
It's the output bit. It was 3rd bit.
Could be, yeah. Although if that's, I should have stated that. So this is quiz 4. Okay, so this is the 3-bit one. Oh yeah, I'm sorry. I mixed some 2 bits with 3 bits in that one. That was meant to make it harder to guess. I think I went a little overboard with that though. But yeah. Yeah, so the answer should be 0 0. Let me double check that. Yeah, 0 0. Yeah. Yeah, I went a little overboard with the multiple choice on that one. Sorry. Okay, this one gives the system Verilog, and then it says, what's the problem with the design? The problem is, this is kind of tricky. If you look at here, you've got the next state logic here. This always block is the next state. I'm sorry, not next state, clocked logic. This is the clocked logic. It just sets the current state to the next state. Then you have the next state logic. That's the combinational logic here. And then down here, you have the output logic. So you have all 3 pieces, except, they're kind of crammed together. And so the problem is, it's a little tricky to see, but if you look at this combinational logic that is implementing the next state logic, it's actually going to end up becoming a latch because it has an if then else, but there's no else at the end, So the better way to do this would have been to have a default next state in there at the beginning, right? Or have an else. All right. Now, what's the point of this question? Well, I mentioned in class that the next state logic, you can use an if then else or an assign with a ternary operator or a case statement, right? So in this case, I use this if then else. But if you use an if then else, you have to be careful. Be careful that you don't make it a latch. Actually, the compiler will generate an error for this because we said always underscore com, right? So it'll detect that as an error. All right, you're designing an FSM to keep track of the mood of 5 students working in the digital design lab. This question came from the textbook. Each student's mood is either happy, the circuit works, sad, the circuit blew up, busy, working on the circuit, clueless, confused about the circuit, or asleep, face down on the circuit board. What's the minimum number of bits necessary to represent these states? So the obvious solution is that you count the number of states, which is happy, sad, busy, clueless, and asleep. So there's 5 states, and so you would say log base 2 of 5 is 3, right? 3 bits. But the problem is that there's 5 students who can all be in a different mood, right? So if you want to keep track of the state of the mood of all 5 students, then the number of possible states is it's going to be essentially, it's going to be 3 bits per student, right? Or another way to look at it is you have 5 states, and you would raise that to the power of 5, right? And then take the log base 2, right? Right? Because if you look at it like each mood is like a symbol, or a character, right? And then you've got 5 of them. So it would be 5 raised to the power of 5, right? 1, 2, 3, 4, 5. Yeah, so 5 raised to the 5, right? It was 125? Or no, 25 rather, sorry. 5 times, or no, that's right, I had it right. 5 times 5 times 5 times 5 times 5, right? Which is 25, 125, 625. I don't know. So 5 raised to 5, right? Yeah, 3125. So if you take the log base 2 of that, is going to be 12, 40, 96? Yeah, 12 bits. That make sense? Right? So there's 2 ways to look at that. You could have, I'm prepared this time. Okay, so you can have log base 2 of 5, right? Which is the number of bits you need to represent one student's mood, right? So that's going to be, and of course you have to round it up, right? So if you round that up, it's going to be 3 bits, right? And then if you have 5 students and 3 bits each, right? Then you could do it with 15 bits, right? So you have a 15-bit state value, and then you just allocate 3 bits for each student, right? But another way to think of this is you've got 5 raised to the 5th power number of permutations, right? Which is, what did I say it was, 3125? And then you could take the log base 2 of 3125, round it up, right? And that's going to be actually 12, right? So the minimal number of bits to track all 5 students' mood is 12 bits, right? And I think that's the answer, right? But you might have said 15 by just multiplying the number of state bits for each student.
That wasn't an option, so.
Yeah. Okay. Okay, this one says, what is the next state logic for S1? S1 is, let's see, S0. If you trace this wire, we've got S0 or not S1, right? So S1, next state is S0 or not S1. Because, S1 is comes back through that inverter. Okay, any questions? All right. So the next topic is timing analysis. So I mentioned beginning of the semester that a logic circuit has a functional spec and a timing spec. So for combinational circuits, the timing spec is how much time it takes to get an output after changing an input. So normally that's referred to as the propagation delay, but actually it's actually, in reality, it's a range of values. The delay through a combinational logic circuit will be in a range. The lower end of that range is called the contamination time, and the upper end is called the propagation time, and I'll talk more about those in just a minute. And then for sequential logic circuit, the timing spec is the minimum clock period, or the reciprocal of that is the maximum clock rate. Okay, and that's often assuming certain factors like a maximum clock skew or environmental conditions like temperature. All right, and I'll talk more about that too. So up until this point in the class, we focused on behavioral, logic behavior, right? You design something in system Verilog and then you test to see if it works. We haven't really done anything about the physical characteristics of the circuit. And the main thing there is delay, logic delay. How well does the logic perform? Does that make sense? Right? Because that depends on what technology that you want to put your behavior on. So you can design your logic behavior in Verilog without worrying about the underlying technology until you go to actually deploy your design on a chip, at which point you then have to worry about the performance of that underlying technology. And there's other things too you have to worry about besides performance. There's power consumption, area, area, real estate, right, which is the size of the chip or the amount of resources that your design requires. But in this lecture, we're going to focus on timing. So I also mentioned too, when we do behavioral simulation, I mentioned this a few times, that there's this basically no delay. So when you look at one of these waveforms in QuestaSim, one of the things that I hate about this is that it's not really obvious where the inputs are, what the inputs are and what the outputs are, right? I mean, typically, I think in this case, A, B, and C were the inputs to the circuit and Y was the output. But you wouldn't know that because, I mean, when you look at this timing diagram, everything, all the signals that change at the same time, right? So for example, in this case, right here where I've marked this one spot, A was 1 and B was 1, and C transitioned from 0 to 1, which caused a corresponding change in the output Y. But when you look at that, it's not clear that Y was an effect of C changing, right? I mean, Y changed because C changed, right? So you would expect that Y would change after C changed, but if you look at this, they're changing at the same time, right? And that's just because there's no delay. This simulation isn't modeling any kind of logic delay, right? It's only modeling the behavior. But as you might imagine, there is a delay. So when you have any kind of a gate, like in this case, we have this buffer. A is the input, Y is the output. When we change A, this is a buffer, so it's just creating a unity function. Whatever the input is propagated to the output. But when the input changes, the output will change after the input changes. And that's typically measured from the midpoint of the transition. Now you might say, like if you look at this waveform, it looks like there's infinite slope here. Like when these guys change, they change instantly. But on a real circuit, it takes time for transitions to happen. So when you go from 0 to 1 or 1 to 0, it takes time. So that's shown here. There's kind of a diagonal line here where that change happens. And when you measure propagation delay through a gate, it's measured from the midpoint of that transition. So the midpoint from the input changing to the midpoint of the corresponding output changing is the delay. Now, why is there delay exactly? What causes the delay? It's caused by the resistance and the capacitance inside the gate. And in fact, it's weird. This is kind of strange. I always thought this was almost hard to believe. But that delay in seconds is literally the capacitance multiplied by the resistance. So capacitance in farads times resistance in ohms somehow gives you seconds. Seems strange, but it works out. So that's called the RC delay. Yeah. So the resistance is like order of single-digit ohms, right? But the capacitance is usually in picofarads, right? So when you multiply those, you get like picoseconds of, that's the kind of delay that you get through this thing, through a gate like this. Okay, but the delay is not just one delay. It turns out that the delay through the gate is actually a range of values. The earliest, the shortest amount of delay you'll have through a logic circuit is called the contamination delay. And the longest possible delay is the propagation delay. So that's like the lower bound and the upper bound for the delay. So it's just a range. The terms are kind of strange. I don't know why they call it. I'm not sure why they use the word contamination delay. It's misleading. It's just the lower bound and the upper bound for the delay through the gate. Okay, so why are they different? There's a lot of reasons. So in an ASIC, transistors that pull the output down to 0 are often faster than the ones that pull up to 1. So the NMOS transistors that set an output to 0, logic 0, often that will happen faster than setting it to 1. But also, in transistor level circuits and in logic gate level circuits, you'll often see different paths from input to output, different length paths, right? Different wire lengths, right? So one, like if there's multiple inputs, that's what I meant to say, right? Assuming you have multiple inputs, like that example I showed before, this was one input, one output, right? But imagine if you have a gate with multiple inputs, then there's different distances between those inputs and the output. So depending on, what I'm trying to say is, depending on which input changes, the output may change faster or slower, right? You guys, does it make sense, right? And also there's temperature variations, and there's several reasons. So if you have a circuit like this where you're talking about not a logic gate, not just a single logic gate, but in this case you're talking about a logic circuit as a connection of multiple gates, you can see in this case we have 4 inputs and 1 output, and one of these inputs, D, only has to propagate through that last gate to affect the value of the output, whereas A and B have to pass through 3 gates, right? So that the longest path through a logic circuit is called the critical path. It's kind of the worst case delay that you'll have from inputs to output. And then of course the shortest one is just called the short path, right? So you have to, this affects, like for example, the contamination delay of this circuit will be determined by the short path. So if D changes and it affects Y, like if D goes from 1 to 0, Y may also go from 1 to 0, right? So if you look at the time from the falling edge of D to the rising edge of, or the falling edge of D to the falling edge of Y, that will be probably closer to the contamination delay. Whereas if you look at the difference between A and B changing and Y changing, that will be closer to the propagation delay, right? Okay. So now the question is, how do we actually put numbers to these? Well, generally you'll have, for example, you may be given the propagation delay of the AND gate, and the contamination delay of and the propagation delay of OR, the contamination delay of OR, right? And so the critical path will be the propagation, the longest possible delay of this gate, and that gate, right? So they have it calculated as 2 times the propagation delay of AND, that's these 2 guys, plus the propagation delay of OR, right? So that's the longest possible delay through the circuit, whereas the short path is going to be the contamination delay of the AND gate. So what I'm trying to say is that the contamination and propagation delay are associated with both a circuit like this and also with individual gates, right? So sometimes you'll be given those numbers for individual gates, and then you'll have to find the propagation and contamination delay for a circuit like this, right? And so, when you do that, then the critical path, which is the longest path, you're going to be calculating that based on the propagation delays of the gates that are along that path, whereas the short path, you're going to be calculating that based on the contamination delay of the gates along the short path, right? Now, the problem with this, though, is the book doesn't go into this very much, but so I added this slide. So the number of possible paths through a circuit increases with the number of fan-outs, right? The internal fan-outs. So that previous one I showed you didn't have any fan-outs, right? Yeah, there's no fan-outs. Every single wire just connects one output to one input, right? But you can have a fan-out where you have an output connected to multiple inputs. So in this case, the output of this gate is fanned out, which means it splits off to the X global output and also to the input to this NOR gate, right? So there's only one fan out because all the other wires are just point-to-point wires, right? But the problem is that even with that one fan out, it gives you 7 possible paths through there, which I've color-coded. There's 7 possible ways to go through that circuit. And so in general, if you start with each input and you count the number of fan-outs from each input to the output, and then you just add them all up, or actually you raise them to the power of 2 and you add them all up. So let's see. So if we look at A, B, and C, each one of those passes through this fan out here, right? Whereas D has no fan outs, it just goes straight through. So you take you take 2 to the power of 1 for A, B, and C, and 2 to the power of 0 for D. You add those all up and you get 7. So there's 7 possible ways to the circuit. As you might imagine, if you have a lot of fan outs, the number of paths can blow up pretty quickly, right? Now, luckily, we don't need to worry about this problem at scale because the tools do it for us. The synthesizer, right? The CAD tools take care of this for us, but they have to do, this kind of analysis to find the long and the short paths, critical paths and the short paths.
Is there a maximum fan out that?
No.
Technology or?
No, no, I don't. Well, maybe there is. I've never. I don't think so. It's a good question. It lists the fan-outs, though. If you look at the reports when you synthesize your design, you can find all the fan-outs. You can find the highest fan-out nets. Obviously, clock is the one that fans out the most because it connects to all the registers. But that clock is usually routed on special wires that are designed for high fan-out. But for regular nets like this, regular signals, you can get a listing of the fan-outs. Okay, so there's because you can have long paths and short paths, and also you have this notion of fan-in as well, because every time you have a gate with multiple inputs, that's a fan-in, right, where you have multiple wires are being combined to get one wire. So if you have a circuit where you have long paths and short paths, and then a fan-in where you combine long path and short path, you can end up with a glitch. So in that case, what that means is that let's assume you have this circuit, and you set A to 1 and A to 0 and C to 1, and then B transitions from 1 to 0. Okay. What will happen is if you look at the truth table, all that means is that you're going from 0, 1, 1, okay, to 0, 0, 1. right? Because B changes from 1 to 0, right? So that actually should not affect the output at all, because both of those rows in the truth table have a 1 as the output, right? So if I change B when A is 0 and C is 1, it should not actually affect the output at all, right? But it turns out that it will, or it may, because B has this fan out here, and it's subject to a long and a short path, right? Because one of the B ends up going through 3 gate delays on this path and 2 gate delays on this path, right? So what'll end up happening there is when you change B from 1 to 0, if you look at these two inputs of this OR gate, we label them N1 and N2, right? Right? N1 will change after N2 because N1 is going to change after 2 gate delays, right? So B has to propagate through 2 gate delays, the inverter and the AND, before it gets to N1. And it propagates through only 1 gate before it gets to N2. Make sense? So if you change B from 1 to 0, that will cause the output of this AND gate, which is N2, to switch from 1 to 0, right? Because previously it had a 1, 1, and we're going to 0, 1, right? So N2 will change from 1 to 0, right? Likewise, N1 is going to change from 0 to 1 because it previously had a 1, 0, and now it's going to get a 1, 1 when B changes, right? So N1 is going to change from 0 to 1, right? The problem is that the N1 and N2 are both changing, but not simultaneously because they both see different delays. Okay, so N1, N2 will change first, N1 will change second, but in between N2 and N1 changing, you'll end up with a 0, 0 on that OR gate, which will put a 0 out, right? So what will end up happening is that the output of the circuit will be 1. It will go to 0 during that interim time when one of the intermediate wires has changed and the other one hasn't changed yet, but then it will go back to 1 again, right? So this is called a glitch. It's when you see a very momentary change and then another change on a signal, right? So there is a way to fix glitches. And I actually don't know if this is works universally, but the way the book has a solution, the book solution is that if you look at what's happening here, if you look at the Karnaugh map, if you remember from 211, this circuit is a sum of 2 products, right? And but not full products because there's 3 inputs, right? So for this to be a full sum of products, each of these AND gates should have 3 inputs, right? But they don't. They have 2 inputs. Why? Because it's a minimized circuit. So this is the Karnaugh map. And the way the circuit is constructed with these gates, you can see that they've chosen to group those 2 1 bits and those 2 1 bits, right? And when you change B from 1 to 0, what's happening is you're going from 0, 1, 1, which is 0, 1, 1 here, to 0, 0, 1 to here, right? So when you think of it on the Karnaugh map, you're causing a jump from one group to another, right? You're transitioning between 2 groups, right? And that's causing the glitch. One easy way to fix that is to just add another group by circling these 2 ones, which adds another AND gate and another input to the OR, right? Adds another term, right? Now this is a redundant term. It doesn't change the logic, But what it does is it makes it so if you go from one group, I'm sorry, you're over here, so you're going to circle this group. So if you change B from 1 to 0, you'll be going from one entry in the kernel map to another within a grouping, right? You're not jumping from one group to another, right? So it adds this extra gate, which prevents there from being a glitch, right? Now, do we care though? I mean, how important is it?
It would have been better just to make it a NAND. The two of them put NAND, and then you would.
Yeah, you could do that. Well, that would be I think that'd be a NOR. Yeah, yeah. You could combine this together into a NOR. Yeah, that's possible. I mean, that might work. But you know, then there may be you may not always be able to do that.
Just theoretically, could you detect this on like system parallel?
Yeah, actually, I don't know exactly how they do it, but sometimes you'll see glitches in QuestaSim.
So it'll just like for a very brief moment, it'll just.
Yeah, it looks like a line. Like even if you zoom into it, like even if you really zoom in on it, it'll just be a little vertical line on QuestaSim. Yeah, you'll see it sometimes. It'll for whatever reason, QuestaSim puts glitches in there. I don't know. I mean, presumably because it detects some condition in your code that would cause a glitch. Yeah. Now the problem is that glitches. It's not really practical to always fix every glitch that way, and it turns out that in most cases it doesn't matter if there's a glitch. Okay, because and the reason why is because generally your combinational logic is in between two flip-flops, right? So when the input flip-flop, when the flip-flop that's providing the inputs to the logic circuit changes, right? Then you have a whole clock cycle before the outputs of the combinational logic circuit need to stabilize, at which point you're going to sample those with another flip-flop, right? This is called the dynamic discipline, meaning that any of those glitches that'll happen are going to happen between the contamination delay and the propagation delay of the circuit, right? And as long as we design the circuit so that we don't care about anything going on between the contamination delay and the logic delay, then glitches don't matter. They're not going to hurt us, right? Make sense? All right. Okay. So now the problem though is that if you have, so you know, generally you're going to have, like you have in your CPU now, you're going to have you'll have a memory element, usually, a flip-flop register, and then you'll have some combinational logic between them, right? And these guys both have clocks, right? And so the idea is that within each clock period, you have one clock period to propagate through this combinational logic and be ready and stable for this guy to get the result, right? To clock in the result, right? The problem is that these flip-flops themselves have a contamination delay and a propagation delay, okay? So the notation here is called, let me go back and I want to point out the notation that's being used here. So notice that it's T underscore CD is contamination delay, is what they're using, and T underscore PD, propagation delay. Now the flip-flops / registers, they will have their own contamination delay and propagation delay. That's called TCCQ and TPCQ. I don't know what that means. I think the Q is like, the output of the flip-flop's usually called Q. And the C and the P is contamination propagation. But I don't know what that middle C is there. I don't know what that stands for, right? But the propagation delay of a flip-flop is relative to the clock. So whenever the clock edge happens, the flip-flop will change its output between the contamination delay and the propagation delay relative to the clock edge, right? So when you get the rising edge of the clock, there'll be nothing will happen at first until you get to the contamination time. And then some crazy stuff may happen until you get to the propagation time, at which point nothing will change again, right? You guys with me? So that's TPCQ and TCCQ, right? Okay. So the problem, though, is also, there's another issue, is that the flip-flops have this notion of a setup and a hold time. Now, this is relative to the input. So the propagation and contamination delay is the, talking about the output of the flip-flop. But the input of the flip-flop has these setup and hold, which means that whatever you're putting into a flip-flop has to be stable for an amount of time prior to the clock edge called the setup time. It has to remain stable for a time after the clock edge called the hold time. And if you add together the setup and the hold, that's called the aperture. That's the aperture time. Okay, I love that because I love that term because I always think of a flip-flop like a camera, right? Where, the clock edge is like the shutter of the camera, right? So, the clock edge goes up, right? For if it's a rising edge, and it's like you're taking a snapshot of the input, right? That's the way I always thought of it. And that's why I like the aperture term. Okay, now what happens if you change the input to the flip-flop inside of the aperture, meaning you change it during the time between the clock edge minus the T setup or the clock edge plus the T hold, right? If you change it in there, the flip-flop might go into a condition called metastability, which means that the output of the flip-flop will go somewhere in between 0 and 1. It'll be at a voltage that's between logic 0 and logic 1. But it won't stay there permanently. It will eventually go to 0 or 1, and then everything will be fine, right? But it'll be in what they call the forbidden zone, right? Between logic 0 and logic 1 for some amount of time, right? And you don't want that to happen. So the goal is to avoid changing any flip-flop inputs during the aperture time. So how do you do that? You have to achieve timing closure. So you have to generate your circuit in a way that avoids that, right? And you do it with knowledge of the delay of gates. So the logic delay of your gates, when I say delay of your gates, I mean the propagation and the contamination delay of each gate, is going to be given to you as part of the technology library of whatever technology, whatever chip technology you're targeting. Okay? So the idea is that you want to make sure that your clock period, which is T sub C, this is the clock period, so rising edge to rising edge of the clock. You want to make sure that the delay of the logic in between, from the logic from starting from any flip-flop and then ending up at another flip-flop, right? That logic needs to stabilize its output within TC minus the setup time. Okay? But at the same time, if it's too fast, if that logic in between those two flip-flops is too fast, then you might violate the hold time. Because what may end up happening is that the logic will propagate through here so fast that will end up changing the downstream. This is like the upstream and the downstream flip-flop. It'll change the input to the downstream flip-flop before the hold time expires, right? So we have to make sure that this logic is constrained. Its contamination delay and its propagation delay have to be, the contamination delay has to be high enough not to violate the hold time. And the propagation delay has to be small enough to not violate the setup time. Okay? Okay, so the rule is that T sub C, which is the clock period, this is the setup time constraint now. If you add together the propagation delay of the flip-flops, which is TPCQ, and that's a technology parameter. You can't control that. That's inherent to the flip-flop design for the technology, right? So this is a part of the technology library, just like the gate delays are, right? So if you take the propagation delay of the flip-flop and you add the propagation delay of the whole logic circuit in between, in that path, and you add the setup time, because that setup time is the extra time you have to leave for setup, right? If you add all three of those together, that has to be smaller than or equal to the clock period, right? Make sense? Now, the problem with this equation is that there's only one of these terms you have any control over. I mean, assuming that you're trying to meet a certain clock. You have a certain clock rate in mind, right? So when like NVIDIA or Apple, they're designing a chip, they have a certain clock rate they want to hit. So that's going to give you T sub C, right? So that's a constant. And then this T PCQ and T setup are also technology parameters. You can't change those. The only thing you can change as a designer is TPD. Why? Why can you change TPD? Because you have some control over what the logic is in there, right? You can minimize it, or you can try different ways to go from behavior to gates, or you can take some logic out, right? Like you can make your pipeline deeper. Like in our CPU, right? Your execute phase does a lot of stuff, right? It decodes the registers, it does the control unit, it uses the ALU, right? That's a lot of stuff in there, right? You might decide to split that into two stages, right? In which case you're doing less logic, right? So because of that, because TPD is something you can control, we want to isolate that on one side of this inequality, right? So this is going to be rewritten. So we have TPD on the right-hand side of this inequality, and we have TC, PCQ, and T setup on the right-hand side, right? Why? Because these three terms together you can't control, but TPD is your, as a designer, that's your constraint that you have to work in. Okay? Okay, so again, if you look at, this is a pretty nice feature, nice figure here, because you can see that after the clock edge, you have this initial TPCQ, right? So nothing happens until the flip-flops actually propagate their output, right? Then you have TPD. So after the flip-flops propagate, then your circuit gets its inputs, and then you can propagate that. And then you have to leave this margin T setup. You have to make sure that you're stable, your outputs are stable, T setup before the next clock edge, right? Okay? There's also a hold time constraint, though. And hold time says that you don't want your logic to be too fast. So the T hold, the hold time, has to be less than the propagation delay from the flip-flop, I'm sorry, the contamination delay from the flip-flop, sorry, that's TCCQ. That's the earliest that your flip-flop will put a value out on its Q output, plus the contamination delay of the circuit. Right? In other words, the contamination delay of the whole path has to be longer than the hold time, because otherwise you'll end up driving your new input into the next flip-flop before it's ready. Before it's ready to get an input, right? And so again, this equation is reorganized where we want to put TCD, which is the thing that we can influence, on one hand side, and the T hold and the TCCQ, which are technology parameters, we're going to put those on the right hand side, right? Notice the clock is not part of this now. The clock period is not a factor here, right? Because this is dealing with after the clock edge, what happens, right? Right after the clock edge. So there's no TC here. Okay, so here's an example then you'll have. So let's say you have this circuit. So you have some input registers, our flip-flops here. You got an output flip-flops. So you've got, like, you know, downstream and upstream. You know, you got the ones giving you the inputs, and you got the flip-flops taking the outputs, right? And by the way, this could also be the case where the outputs of your logic wrap around to these ABCD registers, right? You could have this could be in a loop too. It doesn't matter, right? The point is that anytime you have outputs here of flip-flops driving logic that eventually drives inputs, right? And we're all in the same clock domain, then you have to make sure that they obey the dynamic discipline, meaning that you obey the setup and hold time, right? So let's say that the contamination propagation delay of the flip-flops, which are these two terms, are 30 and 50 picoseconds. The setup and the hold time is 60 and 70 picoseconds. And then we have a per gate propagation and contamination, 35 and 25. Now in this case, we're assuming that all the gates have the same propagation and contamination, which is usually not the case, but we're doing that just to simplify this problem, right? So, do we have a clock? What's our clock? Clock speed. Sorry. We're just finding in this case, we're going to find the maximum clock speed. Sorry. So we're going to find what is the minimum clock period that will achieve, that will meet the setup time constraint, right? Okay. So to figure that out, we need the propagation and the contamination delay of this circuit. So what is that? Well, contamination is pretty much just going to be the contamination delay of one gate, which is 25 pico. And the propagation is going to be the propagation of 1, 2, 3 gates, because I think you can pass through all three potentially, right? A and B, right? The A and B inputs go through A and B to Y, I should say. A and B to Y is your critical path, which is going to be 3 propagation delays, which is going to be 35 plus 35 is 70, plus 35 is 105. So the propagation is 105, the contamination is 25, right? I got that right? Yeah, 105 and 25, right? Okay, so the setup time constraint is, it says that, in this case, we're going to put the clock speed on the one side of the inequality. The clock has to be greater than or equal to the propagation of the flip-flop, which is 50, plus the propagation of the logic, which is 105, plus the setup time of the flip-flop, which is 60. So that's 35 plus 105 plus 60 is 215 picoseconds. Right, so it has to be at least that, if not greater. And that's 4.65 gigahertz, if you take the reciprocal of that. The hold time constraint is going to say, does the contamination delay of the flip-flop, which is 30, plus the contamination delay of the circuit, which is 25. If If you add those two guys up, you get 55, right? So in other words, at minimum, we'll have 55 picoseconds through this guy. Is that long enough to meet the hold time constraint? Well, what's the hold time? 70. So the answer is no, right? So if you get a signal through there in 55 picoseconds, that will cause these guys to see their input change in 55 when they need at least 70 picoseconds of stability. So this violates the hold time constraint, right? The good news about that is it's easy to fix that. How do you fix a hold time violation? You just have to add more delay, right? So you can go in and you can actually add in some dummy gates along the short path, right? So I could put in these two buffers, right? That will slow down the propagation or the contamination delay from the C and D inputs, right? So that's going to add another 25 picoseconds. So we'll have 25 plus 25 here, which is 50. Right? So we'll have 50 picoseconds plus the contamination flip-flop, which is 30. So 50 plus 30 is 80, so we should be good, right? Now you might say, why'd they add one here? Because you have a possible, you have a short path here from C to X and from D to Y, right? So they want to make sure that you go through at least two gates, right? And the reason is because you got that fan out here, right? Okay. So now we should have an 80 picosecond? Yeah, 80 picosecond, which is more than 70, which means we're good, right? Okay, but there's one other thing you have to worry about. All of that assumes that the clock is the same everywhere, that every flip-flop sees exactly the same clock. I mean, they do see the same clock, but do they see, is the clock synchronized everywhere, right? It's not, because you have this thing called clock skew. Because the clock network is so big, it has a lot of metal in it. There's a lot of wires. And those wires create a lot of capacitance along the clock network, which means that the clock, if you look at the clock at different parts of the chip, it'll actually be phase shifted at different parts of the chip. Does that make sense? Right? So the clock, the rising edge of the clock on one part of the chip may come before the rising edge of the clock on another part of the chip because of the capacitance, right? Because, the electrical signal is only moving as fast as you can charge and discharge capacitors. It's not moving at the speed of light like a lot of people think it does. It doesn't. Much slower than that. And because it's charging and discharging, right? And it's doing it, it's having to do that through resistors. There's resistance. So you can charge and discharge really fast, except that the resistor limits how fast you can charge and discharge. So the more charge you have to charge or discharge, and the more resistance that's resisting the charging and the discharging, you get, it increases the time, right? So you have to factor the clock skew into the setup and hold time constraint. The reason for that is because for the setup time, what may end up happening is that the source flip-flops may have a clock signal that looks late compared to the destination flip-flops, meaning that the signals coming out of the source part, the inputs, may be running late because as compared to the destination, right? Relative to the destination, right? So that makes it look like there's more delay than there actually is, right? Because they're getting a late start, right? By which I really mean, if the source guy is phase shifted positively relative to the destination, that effectively lowers the clock period, right? It shortens the clock period because the clock period is not going to be, the left side of the clock period will be late relative to the right side, so it'll squeeze the clock period. So you have to build in the clock skew, which is the maximum shrinkage of the clock period due to skew. You have to add that as another term when you calculate your skew. You guys with me? Make sense? Right? Likewise, for contamination delay, if the source flip-flops are running early, if the clock edge that are triggering the inputs look like they're running early compared to the destination, right? Meaning the clock period is kind of being stretched out, right? Then you may violate the hold constraint because you're giving the inputs a head start, right? They're getting a head start because their clock edge is earlier than expected, right? Relative to the destination clock edge. So you have to consider the skew time as well. But it turns out that practically it's actually really easy. It's a really easy thing to incorporate because all you have to do is add the skew as an extra term in the equation, meaning you give it a little bit more padding. The skew is more padding you have to give it, right? So you just add the skew. So pretty simple. Now that's for setup time. For hold time, on the other hand, what happens is you end up having to subtract the skew relative to the time you're calculating for your contamination time, right? So you calculate your contamination time and you're backing the skew out of it, meaning that you're saying your circuit is maybe faster than you calculate it to be because of the skew. Now, in this equation, instead of subtracting the skew from there, they're adding it to the other side, to the hold time, right? Okay. So let's look at the same, oh, I don't have an example of that. Oh, I do later. Okay, we'll have an example here in just a minute. Okay, so, well, maybe I should, do I have an example? I'll come back to the example. All right, so let's talk about one other topic and then I have an example of this. Okay, so one of the problems with this dynamic discipline is, and when I say dynamic discipline, I mean, basically forcing the CAD tool or the designer to not put too much or too little in terms of the propagation or contamination delay in their logic circuits, right? The problem with that is that assumes that all your inputs are coming from flip-flops. But what if that's not the case? In fact, even in this class, that's not the case. Because we have IOs, right? There's IO pins. We have the FPGA board has those switches. You know the switches you flip? And those switches are going into a flip-flop. Well, technically they're going into your register file, but your register file is comprised of flip-flops when it's generated, right? Is that right? Yeah, it goes straight in, right? It goes into the... Actually, no, it goes into the pipeline register first, sorry. The switches go into your pipeline register, and then they go into the register file. So they're going into a register, right? What happens if user flips a switch within the aperture time of that pipeline register? What happens? What's going to happen? Well, first of all, it's pretty unlikely because the aperture time is in, it's in picoseconds, right? It's a relatively small part of the clock period, right? Right? But let's just say someone flips a switch and you just happen to flip it in the aperture time. Your pipeline register will go into metastability, potentially, right? And there's really not much you can do about that. Now, you might think, well, how likely is it to happen? Not likely with the switch, but think about a network packet coming across the network. There's a lot of those bits, there are a lot of bits coming in from the network and it happens continuously 24/7. And those are all inputs. And when I say inputs, the reason they're inputs is because they're coming in on a different clock, right? Your computer, when it's on the network, is sampling inputs that are being driven by a clock on another computer that's not synchronized to your clock, right? And so there's no guarantee ever that input bits will not arrive during the aperture period of your sampling flip-flop, right? So that's just something you have to deal with. So what happens when you go into metastability? Well, as I mentioned, metastability is a situation that resolves itself with enough time. The way that the textbook describes it is it's like having a hill and you put a ball right on the crest of a hill, right? And it's either going to fall one way or the other way, right? Eventually, right? It can only balance on that crest for so long. The problem is that, while it's on there, you have garbage, data. Not only is it garbage, but it's not even a 1 or a 0. It's not even binary. It's some kind of analog value, right? So the time it spends and the time that you'll be in a metastability is dependent on your technology. And it's a random variable based on an exponential distribution. So the time is just simply the exponential of negative t, where t is how long you're in metastable state, divided by tau, and tau is a technology parameter. That would come from your technology library. Depends on the fabrication technology. Okay. So yeah, t is basically just the how long it's going to be. It's a random variable, right? That determines how long you're in the metastable. So the probability that you get into the metastable is just the aperture time divided by the clock period. So it's basically how much of the clock period will result, how much of the clock period will give you a metastable state if the input happens to change in that amount of time, right? What percentage, right? So T0 is the aperture time, it's the setup plus the hold. And Tc is your clock period. So T sub 0, aperture divided by clock period, is just the ratio of time where you're vulnerable to metastability, right? And it's the probability for a given, if you have a given transition and you don't know when that transition is going to happen because it's coming from an external source, then the probability of that transition getting you into metastability is just T0 divided by Tc, aperture divided by period, right? So every period will have one aperture, right? If you multiply that then by the time it takes to get out of metastability, right? What you're doing is you're saying, what is the chance we're in metastability and that we're still in metastability? What is the chance we get into metastability and that we are in metastability at time t, right? Is t sub 0 over Tc times e to the negative t over tau, right? So this is combining the probability of getting in and the probability of still being there after t seconds, right? Okay, so why are we talking about this? Because there's this thing called synchronizers. And a synchronizer is a way where we can try to protect ourselves against metastability on input pins. It doesn't always work. But the idea is that if you protect all of your inputs with another flip-flop in series, right? So instead of connecting your input pin directly to a flip-flop, put another flip-flop in. That protects you because if the first flip-flop goes into metastability, then you have one clock cycle to get it out of metastability before it then propagates to the next flip-flop, right? So you're protecting one flip-flop with another, and you're going to wait until, if this guy goes into metastability, it has one clock cycle to get out. If it doesn't get out in one clock cycle, then your second flip-flop will also go into metastability, right? Because it'll have a weird input, right? Right?
You
Oh.
just put those on places where there's that chance.
Yeah, wherever you have an input.
Inputs.
Yes. I'm not sure about this, but I think the FPGA input, the input buffers, I think they have built-in synchronizers. I think. Never confirmed that. So it's not something you have to add. I think it's built into the I/O resources. Actually, I want to take that back. You don't have a whole clock cycle. You only have one clock cycle minus the setup time, technically, right? It's one cycle, not a whole cycle. You got to get this guy out of metastability by the setup time, right? So you have a little bit less than a whole clock cycle. Okay, so this way we can calculate the probability that a synchronizer fails. The idea is that you have to say the probability it fails is first the probability that the first flip-flop becomes metastable, which is T0 over Tc, right? And not only does that have to happen, but then that first guy doesn't get out of metastability within the clock cycle minus the setup time, right? So you take the normal t, which is the random variable representing how long you're metastable, and you replace that with tc minus t setup, right? Because that's your limit. That's how much time you've got to get out, right? And that will give you the probability of a failure for the synchronizer, right? Okay, so once you have that, then if you know how many transitions you get per second, so, you know, like for the FPGA, like if you take the switch and flip it, like on your lab 3, you take the switch and you keep flipping it as fast as you can, right? Then you can calculate the number of times you flip that switch per second, right? Then that will become n, right? N is the number of times you flip the switch per second. And you multiply that by the equation, right? So basically, that equation I gave you is the probability the synchronizer will fail on one transition. If you multiply it by n, which is the transitions per second, it'll give you the probability per second that you fail, right? And then, if you take the inverse of that whole thing, it will give you the mean time between failures. It will give you the expected time. Given n, the transition rate, you can calculate the mean time between failures. You can calculate how long you'll go before you get some wonky input on your input pin, okay? So here's an example. So the clock rate here is 500 megahertz, which is 2 nanoseconds Tc. Tau is 200 picoseconds. Remember, tau is just, it's in seconds, but it's a technology parameter. It's a parameter. It's the mean, actually. It's the mean of the exponential distribution, right? I think normally they call that lambda. But anyway, it's basically the mean of the exponential. And then T0, 150 picoseconds. Remember, that's the aperture time, setup plus hold, right? So setup time is 100, which means that the hold is obviously 50, right? We can calculate the hold time. And there's 10 events per second, that's n. What is the probability of failure? And what is the mean time between failure? So basically, you just plug everything in. So the probability of failure, and this is given a single transition, right? So the probability of failure does not involve n. It's just the probability that you'll fail on a given transition is 5.6 times 10 to the negative 6, right? So it's basically 5 chances in a million, right? But then, if you're doing it 10 times per second, then you take the reciprocal of that. You multiply by how many times? 10 times per second, and then you take the reciprocal, and it's 5 hours, right? There's 5 hours between failures expected, right? Make sense? And that's with the synchronizer, obviously. That's assuming you have a synchronizer protecting. Okay, sounds good. I think that's pretty much the whole lecture. I had some examples that I didn't get to, but I'll cover those. I'll cover those next time. But also, there's a quiz. I got a quiz on there too for you to take by Friday.